class number 2. So in today's class, let us study about fundamentals of electronics. All right. So what I will do, I'll start from let's say rectifier circuits. Rectifier circuit. Okay, I hope that you guys have gone through with the diode fundamentals, which I had listed yesterday. All right. Now, before jumping into rectifier circuit, let us quickly recall few material properties of a PN junction diode. Okay. So a diode is a two-layer device, right? It's a two-layer device. Okay. What do you mean by a two-layer device? Two-layer device in the sense the diode is comprising of an N layer and a P layer, right? Okay. So diode is comprising of an N layer and a P layer. Okay. Let's say we will say this is your N layer and this is your P layer. Okay. So N layer is having excess electrons and P layer is having excess holes. Okay. Now electrons are negative charge carriers and holes we say positive charge carriers. Okay. Now what I wanted to ask you is that electrons flow, right? When you provide an external electric field, electrons flow. What about holes? Do they flow? Do they flow just like electrons?
No, sir.
No. Then what are they basically? Because sometimes, even when I was a student, I was also in the wrong notion that plus carriers are holes and minus carriers are electrons. Okay. So if holes are not flowing, then what actually happens? What actually are they?
Sir, electrons jump into hole spaces.
Exactly. So the manner in which the electrons are occupying the empty space is nothing but the hole current. Okay. So Virajit, right? Because okay, fine. So that's a major difference. Okay, so the current is due to the electron flow, and the hole current is also due to the electron flow in a manner in such a way that these electrons, they tend to occupy the empty spaces. Okay, so occupying the space is basically taken as the positive charge notion. All right. So on the N side, you will have excess electrons. Okay. So let's say excess electrons, probably something like this you can draw. Okay. And on the right hand side, you will have excess holes. So excess holes, probably you can draw with plus signs. Okay. So this plus sign stands for vacancy created in the PN junction layer, and the minus sign stands for the excess electron. Okay, you can say excess electron. Okay, fine. So this is basically the what you say the PN junction layer looks like. Okay, fine. Next, you know that a pure semiconductor device is an insulator. Okay, so pure semiconductor always behaves like an insulator. All right, but you do not want insulating property in your circuit. Instead, you want kind of transition property. That is, upon the at the moment when you start applying an external voltage, you want that transition to happen. Okay, the transition is nothing but transition from non-conducting state to a conducting state. Okay, so that's the reason the name semiconductor is given. Okay, so under zero external voltage, the material behaves like pure insulator. The moment when you start connecting an external voltage, what happens is that the material property changes from insulator to conductor state, conducting state. Okay, so insulator to conductor state. Okay, so on that note, it is called as the semiconductor devices. Okay, all right. Okay, now next thing what we need to look at is some of the equivalent circuits. Okay, some of the equivalent circuits. Okay, all right. Equivalent circuits. Okay. What are the two modes of operation for a diode? Will it conduct for all the time, or are there any exceptions for the diode conduction? So when is it going to conduct a PN junction diode? It conducts when anode potential is greater than the cathode potential. Correct. So this is one state of the diode, and it stops conducting whenever the anode potential is made less than that of cathode potential. Okay, what do we mean by, you're able to see the screen, right?
No, sir.
No. Okay. Good. Yeah. So what do we mean by anode potential is greater than cathode potential? It simply means that anode is at higher potential compared to cathode. Okay. On the other hand, for non-conducting state, your anode should be at a lower potential compared to cathode. So the diode has two states, conducting state and non-conducting state. Okay. Now, based on the conducting state and non-conducting state, what you can do is you can plot the VI characteristics, right? So you can plot the VI characteristics. Okay. Now, in the VI characteristics, normally we take voltage as the X variable and the current as the Y variable. Okay. Since diode is a semiconductor device, so what happens is that the moment when you start increasing the forward voltage, okay, what do we mean by forward voltage? Let's say this is your PN junction diode, okay, the symbolic representation. This is your anode, and this side is your cathode, okay. Let's say it is connected to a current limiting resistor, okay, just to protect your diode against overcurrent situation, okay. Okay. All right. So let us consider an external battery, say having an EMF of E volts, is connected in such a way that the positive terminal is connected to anode and the negative terminal is connected to cathode. Okay. Now, as we have seen already, that if you make your anode terminal greater than the cathode terminal, okay, you can say that the diode is forward biased. Forward biased. So under forward bias mode, the diode can be treated as a closed switch, right? So this is your current limiting resistor, and this is your external voltage. Okay. So what we have done, we have replaced, okay, this diode with an equivalent element. And what is the equivalent element for a closed condition? A switch. So that is what is called as equivalent circuit. So equivalent circuit is nothing but selection of meaningful circuit operation based on the physical behavior of the device. So the physical behavior as in when you forward bias a PN junction diode, it is going to conduct. Conducting state is analogous to closed switch state. Okay. So what you can do for forward biasing mode, you can simply replace a diode with a closed switch. Okay. With a closed switch. Fine. Now, on the other hand, this is for FB, forward biasing mode. On the other hand, if you look at, say, case B, reverse biasing mode. In reverse biasing mode, what we do is, let us consider the same circuit symbol for the diode. This is your anode terminal and this is your cathode terminal. Okay, let's say you have this current limiting resistor. Okay, the polarities of the battery is now swapped, right? Swapped as in the negative terminal of the battery is connected to anode and positive terminal of the battery is connected to cathode. Okay, so under this mode, the diode stops conducting. Why it stops conducting? That's the reason I have asked you to go through with the prerequisite content. Can anyone tell me why the diode stops conducting once it is reverse biased?
The increase in the depletion region.
Right. So there's something known as depletion region in a PN junction diode. So when you reverse bias the diode, what happens is that the depletion region, tends to increase. So this depletion region can be regarded as the insulator. Okay, so it is similar to an insulator. So greater the width of the depletion layer, poor will be the conducting properties. Okay, so in the reverse biasing mode, what happens is that the depletion layer thickens up, due to which the diode stops conducting. Now, stops conducting means zero current, right? So what is that equivalent circuit symbol you can bring in to show the open circuit situation? An open switch, right? So for reverse biasing mode, what you can do is you can replace the diode symbol with an open switch. Okay, so closed switch for forward biasing mode and open switch for reverse biasing mode. Okay. Okay, this is plus. Sorry. Yeah, I'm so sorry. That is, I should have changed, right? Polarity. So minus and plus. Okay. Okay. Here, I'll maintain minus, and here I'll maintain plus. Okay. Okay. So here the current is 0 and here there will be a flow of current. Okay, fine. So far what we have discussed is the ideal characteristics, right? Nowhere we have talked about the minute resistance offered by the diode. Okay, so if the diode is forward biased, we simply say that diode conducts and you can replace the diode symbol with an closed switch symbol. On the other hand, whenever the diode is reverse biased, you can replace the diode with an open switch symbol. All right, fine. So this is about the ideal diode characteristics. Okay. Now, in case of practical diode, what happens is that along with an ideal diode, okay, let's say this is your ideal diode, okay, in future let me write ideal diode as ID. Along with, let's say, ideal diode, there will be some resistance associated, right? Okay, now this is called as the diode resistance, okay, let us say RD. It is also called as dynamic resistance, okay, RD. Okay, now from where did we pull this resistance RD? Can anyone tell me? Why do we say there will be small amount of resistance associated with the diode? Why that diode resistance creeps into the circuit? Can anyone tell me? You see, your diode is having a two-layer structure, right? So this is your P layer and this is your N layer. And there will be a small barrier potential. Okay, this is your, or you can say depletion layer, okay, whatever you call. Okay. So this I would say the depletion layer. Okay, depletion layer. Now, this is just the material structure. How will you connect it to an external circuit? In order to connect it to any external circuit, you should provide some contacts, right? So those contact points are called as ohmic points, ohmic contactors. Okay, so let me show these ohmic contacts with the green color. Okay, so these are your ohmic contacts. So let's say this is your anode and this is your cathode. So this green color indicates that they are meant for connecting the diode to an external circuit. This is called as ohmic contacts. Okay, so basically the contact points of the diode adds this resistance. Okay, adds this resistance. Okay, so that's the reason, in case of practical diode, it makes sense to consider even that small ohmic resistance. Okay, so let's consider RD as the contact resistance of the diode. Okay, and rest all remains the same. Okay, so for forward biasing, what you will do, you will connect positive terminal of the battery to anode, and the cathode is maintained at negative potential. Yeah, tell me. Any doubts?
No, sir.
No, this is forward biasing. Okay. Now you tell me what happens when you substitute the diode symbol with the analogous or equivalent circuit symbol. What shape the diode circuit takes place? So ideal diode you are supposed to replace with a closed switch, right? And then you will have the dynamic resistance of the diode followed by the battery, okay? So it appears as though under forward biasing mode, the circuit takes the shape of a resistive circuit, correct? And if you were to plot the response of the circuit, that is E versus, let's say, I, what kind of response you will get? If I were to plot variation in E with respect to variation in I, what kind of response I will get? This is my equation, right? E is equal to I into RD. So what kind of response I will get? A linear response. Now, with this equivalent model, do you think this equivalent model is correct? Or we'll have to introduce some concept into our circuit? What we said, when diode is forward biased, it simply conducts. Okay, the difference between circuit 2 and circuit 1 is that we have introduced the diode resistance, which is due to the contactors. Okay. Now, if you look at the VI characteristics, we get something known as resistor response. Resistor response. So, diode is not a conductor; it is an insulating device, right? I mean, it is a semiconductor. So, the VI characteristic is giving me a kind of conductor-shaped characteristics, right? It is giving me kind of conductor-type characteristics, but my diode is semiconductor. So that means to say something I am missing over here. Okay, some concept, important concept that I am missing over here. Okay, so that concept is nothing but the barrier potential. So what I have done in my explanation, nowhere I have considered the barrier potential. Okay, now what is this barrier potential? So this barrier potential is due to the immobile charge carriers present in the depletion layer. Okay, so this immobile charge carriers found in the depletion layer give rise to something known as barrier potential. Barrier potential. So this barrier potential is different for different material. Okay, so barrier potential normally represented by Vk. Okay, so Vk is sometimes it is also called as the knee voltage. Knee voltage. Okay, what are the different materials that can be used to construct a semiconductor device? Can you tell me? Can anyone tell me? What are the different types of materials can be used to construct a semiconductor device?
Silicon, germanium.
Okay. Gallium arsenide. Gallium arsenide also can be used. Majorly we use silicon and germanium. Gallium arsenide is new material. Okay, we'll come to it sometime later. Okay, fine. Now, if you use a silicon material for the diode construction at room temperature, it is found that the barrier potential lies somewhere between 0.6 to 0.7 volts. On the other hand, a germanium diode gives a barrier potential in and around 0.3 volts. On the other hand, gallium arsenide based semiconductor device gives a barrier potential which is close to 1.2 volts. Okay, so these are the different barrier potentials given by the materials. Okay, now which is the most commonly used material in semiconductor device? Silicon, right? Silicon is most common. Why? Why? Why silicon is used?
Most available.
It is used because of certain technical reasons as well as economical reasons. Okay, so first of all, silicon is easily available. Okay, it is easily available. Okay, easily available in high purity. That is very important. High purity. That is, you have abundant resource of silicon. Okay, and that too with the good purity. So basically, the manufacturing cost can be reduced. So you can construct semiconductor devices with low cost. With low cost. Okay, so that's the first point. The second point is that it is having good thermal thermal capabilities. It is having good thermal capabilities. Okay, thermal capabilities in the sense the ability to handle the higher temperatures. The ability to handle higher temperatures. You see, the biggest difference between semiconductor device and a conductor device is the manner in which the current flows against increasing temperatures. Okay, in case of conductor, what happens is that as temperature starts increasing, what happens is that the resistance of the material will also be increasing, due to which basically current starts reducing because of the internal molecular friction. On the other hand, in case of insulator, this is very important, please make a note of it. In case of insulator, as the temperature starts increasing, the resistance of the device starts decreasing. That's because when you increase the temperature, okay, the electrons which are found in the outer layer, okay, which are not free electrons, somewhat it is bounded to the outer layer, gains sufficient thermal energy, and due to this thermal energy, they will come out of the bonding structure. So what happens is that as the temperature starts increasing, okay, more and more electrons are available for conduction. So when more electrons are available for conduction, what you can say is that somebody has enabled the speaker. Sarang Srikumar,
Yes, sir.
please mute it. Okay. If necessary, unmute and you can talk. Okay. Yeah. So as the temperature starts increasing, more and more electrons are available for the conduction. So when you have excess electrons, you can say that the material resistance starts reducing. So this will lead to something known as thermal runaway. Thermal runaway. Okay. So which is very common in case of semiconductor. Okay. It's not insulator. Semiconductor. I'm so sorry. This is semiconductor. Okay, that's the reason all these CPU fans, etc., is provided, right? You must have seen in your laptops, desktops, etc., the cooling provision is given. That cooling provision is to avoid the excess heating. Okay, because without the cooling, the transistors which are found within your CPU can undergo thermal runaway. All right, so that's the reason. Now, if you compare the thermal capability, okay, you will find that the silicon is having better temperature handling capability compared to germanium. Okay, gallium arsenide actually is having the best thermal handling capability. Okay, so the thermal handling capability of gallium arsenide, okay, I'll put 3 ticks. And for silicon, I will put 2 ticks. And for germanium, I will put a single tick. Okay. So number of, if you find more ticks, it is understood that the better is the material. Okay. So gallium arsenide has the best thermal handling capacity, followed by silicon and then germanium. Okay. Fine. But gallium arsenide is kind of emerging material. That's because of the first point. Okay, in order to produce a semiconductor material using gallium and arsenic, elements, the process cost is very, very high. So that's the reason normally we don't find any semiconductor device made up of gallium arsenide material, simply because of the high material cost and high processing cost. Okay, but in time to come, probably gallium arsenide material will replace the silicon material. Okay, that's because it is having the best temperature handling capability. All right. Fine. Okay. So the summary of our discussion is that the barrier potential you are supposed to consider while constructing the equivalent circuit. Okay. So now let us construct the equivalent circuit. Okay, by considering RD, that is the dynamic resistance of the diode, and also the barrier potential Vk. Okay, so let us use these two elements in our equivalent circuit. Okay, now can anyone tell me the significance of barrier potential? The barrier potential, will it helps the diode in conduction, or will it opposes the diode conduction? Can anyone tell me?
Will oppose, sir.
Opposite, sir.
Exactly, opposes. Why?
Opposes.
The barrier potential is due to the depletion layer, right? So Vk opposes diode conduction. Okay, this is very, very important. You are not supposed to, what you say, having any confusions in this. Okay, always remember Vk opposes the diode conduction. Now let us place the barrier potential in our equivalent circuit. Okay. Now what is the potential value for silicon? It is 0.7 and it is almost fixed, right? So this Vk can be considered as a DC battery. Can be considered as a DC battery having a potential of 0.7 volt. That is because the potential is fixed. It is 0.7. Okay. So you can consider Vk as a tiny battery cell. Okay. So this is your Vk. Okay. Fine. Now let us place this Vk in our circuit. Okay. So first I have my ideal diode. All right. Let us mark the terminals, anode and cathode. Okay. And then I'm supposed to place, okay, the barrier potential, which I'm going to represent with the help of a battery. Okay. And then probably you can just connect. Okay. The dynamic resistance. Okay. Dynamic resistance. Okay. Dynamic resistance. Connecting resistance is pretty easy, right? Because it is a bilateral device. It doesn't matter which side of the resistance you are going to consider. Okay. Now, who can help me in placing this barrier potential? So here I am supposed to place the barrier potential. Can anyone help me? Which side I should be connecting to the
reverse.
Okay, reverse as in, let us say positive terminal of Vk, where I should be connecting it to.
Towards negative to be content. The negative to be connected to the cathode.
Cathode. Okay, so one person is saying negative to be connected to cathode. So you are saying this way, right?
Yes, sir.
Okay. Are there any other answers? Are there any other answers? So let's say, your classmate is saying negative terminal should be connected to cathode. So negative terminal of the battery is connected to cathode. And positive terminal is connected to the, the second element, that is RD. Is it correct? Or do you have any other, proposals? In the beginning, what did we discuss? Vk opposes diode conduction. If we were to place Vk in this manner, is it going to oppose the diode conduction, or will it simply allows the diode conduction?
Oh, sorry, sir. Same direction.
Correct, no?
Same.
Yeah. So the property of Vk is such that it opposes the diode conduction, because Vk is nothing but depletion layer, remember. So if you place your Vk in this manner, what happens? The current flow is in this direction. Okay. Let me close this circuit. Okay, let me close this circuit. Then you will understand. This is plus, this is minus. The circuit current flows in this direction, and the Vk, imaginary Vk, will also be sending the current in the same direction. So where is the question of opposing the diode conduction? It is not opposing the diode conduction. That means to say, what you have marked about Vk is incorrect. Okay, so you have to, what you say, place Vk in such a way that it always gives you the opposing phenomenon. Okay. So let us keep Vk in this manner.
Yes, sir.
This is plus and this is minus. Okay. Now, is it making sense?
Yes, sir.
Yeah, it makes sense, right? Now you see, this Vk, okay, is trying to send the current from negative terminal to positive terminal, which is in opposition, which is in opposite to the circuit current. So you can say that this is the correct equivalent circuit for a diode. Okay, so this is your practical diode circuit. This is your practical diode circuit. Okay, so under conduction mode or under forward biasing mode, okay, under forward bias mode, okay, when let's say E is greater than Vk, what happens to diode conduction? Okay. On the other hand, when E is less than Vk, where E is the external potential, what happens to diode conduction? Okay, you are supposed to tell me the answers in on or off. Two questions I have posed. What if your external potential is greater than the barrier potential? And what if your external potential is less than the barrier potential? Okay. Okay, you can just type the answers in the chat box. Don't worry, I will not give any marks for this. Just an exercise. Okay, so probably if your answer is, say, you can just type it in this manner. I-on and 2-off. Something of this kind you can answer in the chat box. Okay. Okay. So we are getting answers. Good. Right or wrong, don't worry. You are making an attempt, that is important. All right. So let us dig deep into this. Okay. Now, when external potential is greater than the barrier potential, diode will be on. Okay. On the other hand, when your external potential is less than the barrier potential, diode is off. Okay. So I think most of you have got this answer. Okay. So when your external potential is greater than the barrier potential, we say diode is on. And vice versa condition, we say diode is off. Okay. So let us construct the forward bias characteristics. Okay. So to get on condition, E should be greater than Vk And to get off condition, E should be less than Vk. So what we can do is we can draw the axis. Let's say this is your E, and let's say this is your current I. Okay. So you are comparing E with what? With Vk. So what we will do, this comparison factor, let us place on x-axis. Why x-axis? Because Vk is potential, right? And potential is projected along the x-axis, and this is your current. Normally, it is in millis of amperes. Okay. Now, if your current, if your external voltage is less than Vk, you said the diode is off. Okay. What do you mean by off? Off means current is 0. Okay, current is 0. Okay. So let's say, let me write here. Here, I is equal to 0. Okay. On the other hand, when E is greater than Vk, we say diode is turned on. And when the diode gets turned on, what happens to the equivalent circuit? So when D is on, the equivalent circuit takes the following shape. So this is your barrier potential, okay, and this is your RD. This is plus and this is minus, and this is the flow of current. Okay, so basically, for on condition, you are left with RD. And what is the response of resistance against current? You have already seen. You get a linear response, right? See, this is equivalent to this circuit. Okay, of course, there is a barrier potential that we have already considered, right? Because till barrier potential, current is 0. Beyond barrier potential, there will be a flow of current. That is what we have explained, right? Now, if you consider the relationship between the current I and voltage E, okay, for a resistive element, we see that we get linear characteristics. So what you can do, the same linear characteristics you can draw beyond Vk, beyond Vk. So this is where you get I. So I is equal to some diode current ID. Okay. So this is your practical diode characteristics. This is your practical diode characteristics. Okay. Reverse bias. Okay. Reverse bias. Actually, what happens is that under reverse biasing mode, the current flow through the diode is very, very small. Practically, the reverse current is in the order of nanoamperes to picoamperes. So for that nanos to picoampere, range, you can say that the diode behaves like here. I is approximately 0 amperes, and for here the scale is normally in nanos of amperes. Okay, only when your applied voltage exceeds something known as breakover voltage, breakdown voltage, okay, that is this breakdown voltage, there will be it approaches infinite amperes. That means to say current will be very, very high. Yeah, and that can destroy the circuit. Okay, so this is your forward bias characteristics, and this is your reverse bias characteristics. Okay, so this is your practical diode characteristics. All right. Okay. So this is the practical diode characteristics. Okay. Now, sometimes, we go for approximation. Approximation. Okay. So this approximation gives you something known as first approximation equivalent circuit. first approximation equivalent circuit. So in the first approximation, what we do is, we can neglect this VK. Okay. No, I'm sorry, not VK is neglected. Okay, VK is not neglected because that's the barrier potential. In first approximation, what we can do is we can neglect RD. So RD is neglected. Okay, that's because RD is very small. Okay, up to few ohms to about 20 ohm, few ohms to maximum 20 ohm. You will get the value of resistance. So considering this being a very small resistance value, it is possible to neglect the resistance effect. Okay. So in exam, what you have to do is you have to read the question carefully. Okay. So if they have given you the resistance value, let's say RD is equal to 5 ohm they have given. If given, you consider this model. If given RD value, consider this model. Okay. If they have not given any resistance value, then you can go for this first approximation circuit. Now, if you neglect RD, what kind of circuit you are going to get? You will have the anode and cathode terminal. Okay, this is your ideal diode ID, followed by the barrier potential. Okay, now you know the logic behind the placement of plus and minus signs of VK, right? Okay, and this is your, external circuit. Okay, let's say some current limiting resistor. Okay, RN. Okay, and when when E is less than VK, you know that ideal diode is off. On the other hand, when your external voltage is greater than the barrier potential, your ideal diode will be on state. So for on state, what you get is something of this kind. Okay, this is E and this is VK. Okay, so for this particular circuit, okay, what kind of VI characteristics you will get? What will be the VI characteristics? Can anyone tell me? I can draw the VI characteristic right here itself. Okay, if you neglect the resistance effect, your graph will be something of this kind. Okay, so this shape you will get for RD, and you will get this shape if RD is assumed as 0 ohm resistor. Okay, and we can assume RD as a 0 ohm resistor or a short circuit equivalent because practically, if you look at the RD value is very, very small. Okay, so the orange color, stands for first approximation. So this is your first approximation. Okay, on the other hand, this red one, the slanted line is your practical circuit. Okay, and first approximation is nothing but the derivative of the practical circuit. Okay, so summary. Okay, so the summary is that you have to select either of the two. Either you have to select the exact practical circuit, or you have to select the approximation circuit. Okay, so if RD is given, then your equivalent circuit should be of this kind. Okay, this is your RD. If RD is given, this should be the diode equivalent circuit. On the other hand, if RD is neglected or not given, you can select the approximate circuit. This is anode, this is cathode. Anode, cathode. Okay. And finally, if let's say RD and VK is not given, then what will you do? If RD is also not given, or you have been asked to neglect both RD and VK, so what will you do? Or what type of diode model you will get? You will get ideal diode model. Ideal diode model. Okay. In case of ideal diode model, can anyone help me in plotting the characteristics? Ideal diode model, what kind of characteristics you may get? So this is V and this is I. In ideal diode model, what happens is that, okay, in ideal diode model, what happens is that when diode is forward biased, okay, for forward bias, okay, it's okay, I can come down, don't have to see, let me redraw. Okay, for ideal diode model, for forward bias, this is your diode, okay, ideal diode, and there is no resistance whatsoever. You will just have a battery, okay, and this is your circuit current. So what will be the value of I? Infinity amperes. That means to say very, very large. Since there is no barrier potential, so what happens is that the moment you connect an external voltage, the current almost rises to infinity instantly. Okay, almost instantly the current rises to infinity. Okay, so this is your forward bias characteristics. And in reverse bias, okay, this is for forward bias. For reverse bias, okay, the diode acts like an open switch, right? The diode acts like an open switch, okay? So current is equal to 0. This is your negative voltage axis. Okay, so current is 0. I is equal to 0 amperes and I is equal to infinite amperes. So this is your ideal diode characteristics. All right, fine.